the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for linear algebra students who've just been introduced to transformations. You've just finished my video on the definition of a transformation, and I went through a couple concepts of transformations. In this video, we're going to now define the actual machine that causes a matrix transformation. I want to state from the get-go here that not all transformations are matrix transformations. This is a subset of transformations. Just like not all functions are trigonometric functions. There are definitely a ton of other functions that are non-trigonometric functions. Along the same lines, matrix transformations are just a subset of all the different kinds of transformations that you'll encounter in mathematics. They're just the ones we're going to deal with the most in linear algebra. All right, so when it comes to matrices, the transformation we are interested in is the transformation that takes the vector x and transforms it into the product a times x, where the range of the transformation is the set of all linear combinations of the columns of A. Now let me just piece that apart a little bit to make it more understandable. The transformation machine that we're interested in linear algebra commonly, there are other transformations we'll talk about, but the one we're interested in mostly is the one that takes a vector, and this vector might be an Rn, and let me call the transformation T, and it maps that vector into a brand new space, or could be the same space, Rm. Remember, the matrix vector product is a brand new vector. We've seen that over and over again so far, right? The matrix A times the vector X tends to be some vector B. Not tends to, it's actually some vector. So that should make sense to you. The range of the transformation is the linear combinations of all the columns of A. And the reason why we say that is, remember, X is just some random vector in Rn. If we call X the vector X sub 1, X sub 2, all the way to X sub n, then we know from our previous work in linear algebra so far that the matrix vector product is just a linear combination of the columns of the matrix A, with the weights being these corresponding values in X. And that is why that last part of the sentence says, where the range of the transformation, the set of outputs, is all linear combinations of the columns of A. Because we are allowing X to be anything we want, it's all possible linear combinations of the columns of A. And just to bring back a definition that we've been using, I constantly want to wrap back the things you've learned in your linear algebra course, and so it's worthwhile to say it here. The set of all linear combinations of these columns is called the span of A sub 1, A sub 2, all the way through A sub n, because it's all possible linear combinations of those column vectors of A. So there you go. That's just the concept of what we're doing here when we have matrix transformations, and it'll become very obvious how to work with them because they're pretty easy to work with. For example, define the transformation which maps r squared into r cubed. We're going to define this by the transformation T of x is equal to the matrix A times x, where A is this constant matrix here. So that's the rule of the transformation. In the previous video, I described a transformation. The transformation I described there was take twice the first entry and 0 times the second entry, and that's what all your vectors in your input or domain will transfer to in the range. Well, here we finally have a mechanical look at the transformation. It takes this matrix A and multiplies it against whatever vector you're plugging in. For the time being, ignore U, B, and C right here. We're going to use those in our examples, A, B, and C down there. In fact, let's go ahead and start right now by finding the value of T of U. Well, by definition, T of x is just the matrix A times x, so T of U must be the matrix A times the vector U. Replacing A and U with their component definition here, we get to this point, and now we just need to perform a matrix vector multiplication. There are two ways to do this. I have a video on matrix vector multiplications that if I do something here and you're lost, you can go back to. One way is to consider the matrix vector multiplication as a linear combination of the columns of the matrix, where the weights of the linear combination are the corresponding entries in the vector. But a better way for us to do matrix vector multiplication is via the dot product. Now, normally dot products are defined to be vector-vector products. And I had it in one of my videos. I think the video is called Computation of A times X or something like that. Not that big of a deal, but the dot product itself just takes two equally sized lists of numbers and returns a single number. And what you would do to perform the dot product is you would take this vector and you would tilt it on its side, and you would apply through multiplication that vector to this list of numbers, that row of numbers. And then you would do it again through a product, -2 times 4 and 3 times 5. And finally, one last time, again through a product, -2 times 6 and 3 times 7. And in each of those cases, you would add up those results. Again, I have a video on it, and I think it's in the Computation of AX video, but I'm not 100% sure about that. Anyhow, in any case, you get down to this guy right here, and performing the arithmetic now, we get the three-dimensional vector 4, 7, 9. Remember, we plugged in a vector that was in R squared. We ended with a vector in R cubed. This would be the image of u under the transformation t, or most of us would just say it's the image of u, because technically we are probably already all working with the transformation t, and so there's no point in saying under the transformation t. So I hope that's pretty understandable. I'll cross this off right here, and now we're going to go into part B. Part B says, find a vector x in R squared whose image under t is the vector b. And there's the vector b right there. So I would like to solve the equation t of x is equal to b. Again, very familiar structure here. If you were thinking f of x equals some value 10 or something like that, it's the same idea, except we don't have a division process when it comes to matrix vector arithmetic yet. So what I'm going to do is trade out that transformation on the left-hand side for what the transformation actually is. Remember, our transformation is a times x. So I'll go ahead and trade out that transformation t of x for a times x. And we want to solve this matrix equation. And we've done this so many times that I'm just going to jump right into it. I'm going to build an augmented matrix and use row reduction. Now, offhand, we don't know if there's a solution to this, but we're being asked to find what is the solution, what is x, what is the vector whose image is going to be 7/2, 8, 11. So let's go ahead and start doing row reduction techniques. And we get to this right here. I'm also going to go ahead and clean up this second row right here by dividing it by -3, just because I want to. It's actually for a reason more than just because I want to. It's because we want to find out exactly what x is. And so we're going to go ahead and get to reduced row echelon form. That's the best way to find out a true solution to a matrix equation. I want to pause right here for two reasons. The first being the fact that a lot of students think if you have a row of zeros in an augmented matrix that you have an infinite number of solutions. I'm going to tell you right now, there's not an infinite number of solutions to this system, the linear system we started with, or the matrix equation, I should say. So please let go of the need to think that a row of zeros implies an infinite number of solutions. That's actually not true. What implies an infinite number of solutions by theorem is if, one, you don't have a pivot in the rightmost column, which we don't, and two, if we had any free variables, then we'd have a consistent system with a free variable, which means we'd have an infinite number of solutions. However, we have a pivot in column 1 and a pivot in column 2. There are no free variables, so this system's consistent because it does not have a pivot in the rightmost column, And because it doesn't have any free variables, the system has only one solution. Existence, from the fact that there's not a pivot in the rightmost column. Uniqueness, because there are no free variables. All right, continuing this down, I'm just gonna finalize the row reduction here. And there we have it. So we know the solution is going to be x sub 1 is equal to a negative 1/2, x sub 2 is equal to 2. Or in other words, the vector that solves this matrix equation right here is the vector negative 1/2, 2. Again, the original question was find a vector x in R squared, which is what this is. It's a vector x in R squared, whose image under our transformation is b, and b is 7/2, 8, 11. Row operations do not change solutions, so we are able to do row operations and we get down to a solution. So there we go. We've actually solved that one. Finally, the last question is determine if the vector c is in the range of the transformation of t. And that's kind of like example B there. You just have an output vector and you're wondering, is that output vector in the range of our transformation? It's actually going to be the same mechanics here. And I'm wording it in such a way to kind of match the language in part C. Determine if C is in the range of the transformation T. That is there a solution to T of X is equal to C? That is, we want to try to solve the matrix equation AX equals C. And I like this example for two reasons. One, it's just a good language example, but two, it's really indicative of where we want to go in the future in linear algebra. We're going to have to perform all these same elementary row operations over again with a different right-hand side vector. And that's kind of annoying, to be very honest with you. So in the long run, what we'd like to do is not have to perform elementary row operations like this a second time if somebody comes in and changes the right-hand side like we've done. We'd like to have some automated way of saying, well, all I need to do is do elementary row operations once, and if you change the right-hand side, I will know how to change that solution accordingly. And just to kind of do a bit of a reveal, that's called an inverse matrix process. We don't know how to do it yet, but we will know how to do it in the long run. It's a little more convoluted, so it's better that we don't dive into it at this point. But let's do some matrix operations here, or some row operations. Notice that when we get down to this point right here to do the elementary row operations, well, that's something I already knew. That's going to be the same elementary row operations that we performed before. You're always going to perform the same exact elementary row operations. So again, that kind of goes along with what I was saying earlier, which is, man, I wish I didn't have to do these twice because it's the same stupid operations. The second thing I want to note is that what we just got down to is going to be really close to what we had at this step previously. Notice we had a 1, 2, 7/2 because the right-hand side vector was slightly different. 0, -3, -6, and a 0, -5, -10. Note those last two rows and notice the last two rows here. They're close, but not the same. This is not a -10. And this is what's going to cause an issue. And I'll say it simply, it's because rows 2 and 3 are not multiples of each other. You'll see it in this step. And we get to where we have a pivot in column 1, column 2, and column 3. And that column 3 is the rightmost column in an augmented matrix, which means the system is inconsistent by theorem 2. And that's what I say right here. If you're wondering what I mean by theorem 2, I keep a critical theorem list at the start of every section for my students, and these are just theorems that we have gone through so far. Not all of them, actually. I've erased quite a few, but they're the major theorems that you kind of use throughout linear algebra. And in this list, there's a theorem 2, it's right down here, and you can see it's actually a two-parter. The second part's on a different page. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot. Therefore, if you think about the contrapositive form of this, which I have right here, a linear system is inconsistent if and only if the rightmost column of the augmented matrix is a pivot column. So that's what we're using in this situation here. Since the rightmost column is a pivot, there's no solution to the linear system. And remember, linear systems and their associated matrix equations and vector equations all have the same solution. So if this is inconsistent, then there's no solution to this matrix equation. So the answer to this question, is there a solution to this, is no. And the answer to the original question, which is determine if C is in the range of the transformation of T, I'll just point and arrow and say it's not, because it's not an output of A times X. There's no solution to AX equals C. Now that's a pretty good example, pretty complete actually, but I have one extra example, mainly because I really love this topic, and I think the more practice you get and the more examples that you see, the better you can be with this. And the example is the following. In image processing, which is basically what you do when you go to Photoshop, there are transformations to turn off individual pixels, mute colors, blur areas, or striate specific regions. One such transformation is transformation X transforming to the vector AX, where A is the constant matrix that you see here. We will explore the transformations of images later in this course, but for now, let's apply this transformation to any vector you want, just to see. So I'm going to go ahead and apply this transformation. I tell you what, you make up a vector on your own. I'm going to make up a vector. I'll use the vector U here. The transformation, T of U, is defined to be A times U, and A is the matrix that you see right there, and then the vector U we've just made up is this guy right here. I'm going to perform the dot product multiplication, also known as a scalar product multiplication. So I'm just lifting up this vector, putting it on sides so that I can see my multiplications. I'm just going to multiply this against 0, this against 0, this against 1, and add that product together. Then I'm going to multiply this against 0, this against 1, this against 0, and add up those products. Finally, I'm going to take this -1, multiply it by 1, take that 2, multiply it by 0, take that 3, multiply it by 0, and add up those products as well. Now, what happened to this vector? Well, if you say that the first and third positions swapped, you would be absolutely correct. You can actually do this in general. So if I took T of, let's just say, a general X vector, and if I were to perform the scalar product on the rows there, x1 times 0 plus x2 times 0 plus x3 times 1, and then x1 times 0, x2 times 1, x3 times 0, and finally x1 times 1, x2 times 0, x3 times 0. And you can see that no matter what vector I have multiplied against A there, it turns out that it flips the roles of everything within that vector. Instead of going x1, 2, and 3, it goes x3, 2, and 1. That's kind of a cool transformation. While you may not think that's cool yet, just think about what happens with an image if that was a bunch of pixels, which it is on your screen, a bunch of pixels, and if I were to multiply it by some transformation matrix A, so let's say I have some A multiplying that did something very similar to what we did to that vector, the product would flip all the roles of that vector and provide you with this picture right here. And that's actually the behind the scenes mathematics of what's happening in Photoshop. You're just doing a bunch of matrix multiplications, not matrix vectors, but matrix in those cases. But still, you'll learn that in this linear algebra course. It's really cool stuff. And then you can blur, and you can do things like striate patterns and decolorize, all this other stuff. But anyhow, that does it for this video. I hope I've piqued your interest to continue in linear algebra. I hope I haven't driven you away from linear algebra. And I hope you have a wonderful day. Be an awesome person.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.